right. Welcome everyone to well, it's not the first MLOps in person, but one of the hopefully the beginning of many. Like I started off by saying, we're really hopeful that this is like a very interactive session where like people get to discuss. Joe's given us permission to plug in with as many questions as possible, and hopefully it'll lead to a lot of collaboration. Our speaker today is our very own Joe Shinoda. He's a PhD student advised by Dr. Thomas Lee and Rob Nowak. He's a very, very cool dude. I have played basketball with him multiple times and gotten destroyed by him. He also happens to study deep learning theory in his free time, and he's going to tell us a lot about vector valued variation spaces and width bounds for deep neural networks, and hopefully give us insights on weight decay regularization.
All right, perfect. Thank you, perfect. Yeah. So like the title says, this is going to be about vector valued variation spaces and some new results on bounding the number of neurons we need for deep neural networks. And all this is in the context of training with a very popular form of regularization known as weight decay. And this is joint work with Rahul Pari, who's at EPFL, and my advisors, Kang-Won Lee and Rob Noah, whom I got to learn a lot from, which is great. So, okay, I'll get right into it in terms of motivations. So why do we care about vector valued neural networks? So if you're familiar at all with like deep learning theory or like the study of why neural network works well, there's a lot of literature on shallow neural networks with a single output, explaining what type of functions they learn, why they work so well, what is their advantages over like kernel methods or linear methods. But the problem with all this stuff is that it's really hard to go from shallow neural networks to deep. And the real mystery is in depth, right? That's where we're seeing all these great advancements in AI and such. So studying vector valued neural networks gives us sort of the stepping stone to get to understand deep neural networks, because a deep neural network is really a composition of vector valued neural networks. And this is also important for like multitask learning networks. And it's huge because most of the time you do things like multi-class classification, like MNIST even, right? Okay, so that's why we want to study vector valued neural networks. We saw a bit of a gap there, and that was hindering us from going to the deep case. And then the second thing that this talk really focuses on is weight decay regularization. And weight decay is a very popular explicit form of regularization, and it's very easy to implement, but it has a lot of effects on how well you generalize, especially when you don't have that much data. So it can do a lot of work for you in terms of getting you that extra boost in accuracy, let's say. Okay, so some background. So I'm just going to go over a couple of terms that I'll be using throughout the talk and make sure we're all on the same page. So I'm considering a vector valued neural network, which goes from R little d to R capital D. And I'll be training this neural network with weight decay. And what weight decay is doing is so when you train with weight decay, which is usually something you're doing in the optimization of the neural network, what that corresponds to is minimizing some data fidelity loss plus the sum of squared weights. So I'll explain what I mean by that. So suppose I'm training with weight decay. What that means is when I'm doing gradient descent or some variant of gradient descent, maybe, I'm getting my new iterate by stepping in terms of direction of my gradient, and then also attenuating a little bit by some smaller scaled down version of my current iterate. And what this corresponds to is basically just minimizing this objective, this loss, where you have an extra regularizer on all the parameters, and that regularizer is just the sum of squared weights.
Is that always implemented in practice where like the weight decay parameter gets multiplied by learning rate as well?
I'm not entirely sure. I think maybe it might be, but either way, I mean, it's just a matter of scaling the parameter correctly. But yeah, I just wrote it this way so it's super explicit, because sometimes people would ask me like, this lambda doesn't actually correspond to this lambda here. It's really lambda.
Exactly.
Yeah.
Because like, what I'm thinking about is like, I could implement weight decay as just adding that term to the loss, but like, I know that in Python, those two are not equal.
Yeah, you have to account for the scaling. Yeah. But essentially, modular scaling, that's all the same. Yeah. So what you're doing is you're trying to actually minimize, you're trying to get a good fit to your data, and you're also trying to do so with the smallest sum of squared weights on all your parameters in the model. Okay. All right, so the second formulation, which I call the weight decay objective, that's what I'm really going to be talking about when I'm talking about weight decay in this talk. So I'm not really focused on the optimization part of it. I'm focused on what you're actually trying to minimize or what you're doing. Okay, so the second thing that's going to come up a lot in this talk is the concept of homogeneous layers. So let's say I have a neural network that looks like this. This is just one hidden layer. I'm basically doing some kind of linear combination of these representations that I've learned in the intermediate layer. And I'll say that this layer is homogeneous if the activation function involved in this layer, and activation function can be even a linear activation function, it's just identity. It's homogeneous if I can scale the input of the activation function, and that scaling basically just pops out. Okay. And so then I can play this game where I scale down the input and scale up the output and retain the function exactly this. Okay. So that's what I mean when I say homogeneous layers, and that's what I mean when I say weight decay, regularization. Okay, so with both these concepts or ideas in mind, I'll present like the first kind of useful theorem that drives a lot of the results in this work, which is the neural balance theorem. So the neural balance theorem is a very simple result. I think it was first like really written down in Liu's paper, and later in Rahul's survey paper in IEEE Signal Processing magazine. So what's the result? Basically says this: let f be a function, f parameterized by theta, be a function represented by a homogeneous deep neural network that solves the weight decay objective. And by homogeneous deep neural network, I mean literally any deep neural network architecture, transformer, CNN, recurrent neural network, a regular MLP, but it has some layers in there that are homogeneous. So that can be linear layers, that can be ReLU layers, leaky ReLU, etc. So let f theta be that function. For simplicity, I'll just consider like a shallow ReLU neural network. So it's of this form and it solves this objective written out more explicitly with the input weights and the output weights. Then for any neuron with input weight WK and output weight VK, we have that the L2 norm of both those guys are equivalent. And this is what we call the balanced criterion. Yeah.
F has W and V as subscript. You had theta.
Yeah, it's W and V. Yeah, so theta is just W and V put into a very big number.
So this F should have W and.
Yeah, exactly. Yeah, sorry about that. Yeah. So is that clear? Yeah, and this is actually not too hard to show. You can, the way you'd prove it is basically just saying, suppose I have a function f and I want to consider all possible different ways I can do this scaling game, right? Because I know that I can scale the input weights and scale the output weights accordingly and retain the same function. So what choice of scaling should I pick such that it minimizes the regularization term at the end? And if you do the math, you find that turns out the best scaling to take is one that ensures that your input weight and output weight are exactly equal.
Do biases make this messy at all?
So yeah, I'll note on biases. Everything that I'm talking about here works for biases. In the paper, we do have everything with biases. We append a 1 to like the input.
Okay.
But here I'm just going to do without biases because it makes the notation a bit cleaner. Yeah.
So the theorem requires at least one of the layers of the layer of DNN is homogeneous, right?
Yes.
Not all, but just one.
Just one. Yeah. Any homogeneous, actually any homogeneous neuron even doesn't have to be like all the layers.
So then any weight before that is equal to any weight.
Yeah.
After that, in
So
terms of norm.
yeah, for that particular neuron or unit, whatever you want to call it, the input weight going in, the 2 norm of it is going to be equal to the 2 norm of the output.
Hey,
Yeah.
can I ask a question?
Yeah.
Yeah, so have you tried to, empirically train some network and, how long does it take for it to actually see this balancing phenomenon? And is it necessary for the neural network to reach a good accuracy by training so long, or does it just work well before this happens?
Yeah, that's a good question. So in practice, you usually don't actually train a neural network to get it down to the global optimum of this objective, because it's non-convex and you have a lot of issues. Usually you keep training till your validation loss is small enough and you stop. But Jeepan, to your point, there are some papers, and maybe I can point them to you later. There are some papers where people have actually looked at this and seen empirically for large scale models that this phenomenon does happen, that you do get balancing. I'm not sure exactly how long it takes, but it does take quite a lot of time. Yeah, it's not like what you would normally see if you just train a neural network regularly. Good?
Yes, thank you.
Okay, great, thanks, yeah. All right, cool. So any more questions on this? So this is kind of the main, this is a big staple in this talk. It's gonna follow us till the end. So make sure it's clear. Okay. So with this theorem in hand, it's actually a very powerful result. We'll get to see a lot of, I'll just go to the next slide. So what I'll talk about now is what I like to call the secret sparsity of weight decay. So if you look at weight decay, it's L2 norm regularization, and we know that L2 norm doesn't induce sparsity, right? It just doesn't, right? So because of this neural balance stuff, we can actually show that training a neural network with weight decay corresponds to learning something that's sparse, and by sparse, I mean sparse in the number of neurons. So because of the neural balance theorem, we have that this objective weight decay at a global minimum is going to attain the same objective value as this, what I call path norm with regularized problem. And the reason for that is that if WK and DK, the two norms of those things, are equal, then it becomes exactly equal to this term here. So at a global minimum, those two will be equivalent in terms of the objective value that they attain. And now, because of the homogeneity of these ReLU neural networks, what I can do is I can actually enforce that all the input weights lie on the sphere and push that scaling out to the output weights. And then what I get is this new problem, a regularized problem, a constrained problem where the input weights have unit norm and the VKs are free to be whatever they want. And I can go from, if I get a global optimum for this, I can make it, I can make sure that this objective is equal to this objective, and then I can constrain the weight so that it's also equal to this objective. And moreover, I can go backwards. So I can rescale things to go from what I call the group lasso regularization to the weight decay, and from the path norm to the weight decay. So all these things can sort of be played around with. You can go from one formulation to the other at a global minimum.
Should that be an argument then in the last one?
No, I'm talking about the minimum. The objective value of the V.
Then you have to have a scaling factor, right?
Yeah. The VK has to be scaled accordingly, yeah. So this last formulation, I'll call it group lasso regularization. And group lasso is known to induce sparsity, but in the block sense, right? So you're killing out entire blocks of your vector at a time. Okay, cool. So is this clear? Call this the secret sparsity of weight decay. All right. So now I have some motivation. I've told you guys about some of the key results that we'll use, and now I'll talk about what we did in this work and an outline of the contributions briefly. So in this work, we do two things. First, we define a new variation space called the vector valued variation spaces, and we prove a representative theorem showing that shallow vector valued neural networks trained with weight decay solve the data fitting problem over the VB space. Okay? And then the second thing we show is we provide new bounds on the necessary width for any homogeneous layer of a deep neural network. So we provide tighter bounds on the necessary width for any homogeneous layer of a deep neural network, and that number of neurons you need, or the width, only depends on the rank of the internal features. So in a way, it's like data dependent bound. Okay? All right. So let's get into VB spaces. So what are these VB spaces? So let's consider again just a shallow vector valued neural network of this form. Like I mentioned before, we have this homogeneity property. And so what we can do is for any neural network, any ReLU neural network like this, we can always re-express it as the following. We can always re-express it as a neural network where you have some kind of output weight and the input weight lies on the sphere, right? So this formulation expresses all possible neural networks you could want, right? So now let's just consider neural networks that have input weights lying on the sphere, and I'll take my number of neurons to be arbitrarily large. That's going to be k, and make it bigger and bigger and bigger up to infinity. And now my VB space is just going to be the set of all possible neural networks where the norm, what I call the VB norm, is less than infinity. So it's some kind of controlled, you have maybe infinite number of neurons, but they're sort of controlled in terms of how big they can get. And this VV norm is placed on basically a vector measure. So the way we're parameterizing these neural networks is by this vector measure mu. Basically, it's a vector valued measure. So you have things you know about measures. Just think about if the measure now doesn't output a scalar, it outputs a vector. But the only important thing that you really need to know, the details are kind of in the paper, but the important thing is that this VV norm, if you apply it to a finite width neural network, then what you get out is this group lasso type of norm, which we saw earlier a couple slides ago, is in a way connected to weight decay. And that's the key point, okay? So by defining this new variation space, we have a really explicit connection between weight decay and this space of functions. And I'll make that connection more explicit. I'm just hinting to it now. Okay, so now we have this new space of functions parameterized by these vector measures. And so how does this relate to neural networks, and how do we know that optimizing over this space of functions necessarily will be a good thing to do or the right thing to do? So we have a representative theorem, which basically tells us for any data set xi, yi pairs, where these are now vectors, and any lower semi-continuous loss function L, so think of like all the loss functions that you're familiar with, loss entropy loss, MC loss, etc. There exists a solution to this problem written in variational form that admits the following representation, which is exactly a neural network with k naught neurons. And the important thing here is that the number of neurons you need is less than or equal to the minimum of either n squared or n times d. And so why is this important? It tells us that even if you have, so you have any data, you have infinite number of neurons that you can, or you have functions that are potentially infinitely wide, I can get away with fitting this data perfectly with only a finite number of neurons, provably. Okay, I don't need infinite width, basically. And the number of neurons that you need is bounded actually only in terms of the number of data points you have. So if n is really large, or sorry, if d is really large, then this minimum becomes just n squared, right? So for large enough d, the number of neurons you need is completely independent of the dimensionality of your both input and output dimension.
And this for like arbitrary data.
Mm-hmm.
How is it? Like, what's the intuition behind it not having any dependence on like how close the data is about it? Like, if I have like a very, very like discontinuous or very non-smooth count data, but I have like points that are very close to each other, but the labels just keep flipping. That's a very difficult function to fit, right?
I mean, yeah, but you need a lot of neurons,
So
right?
I think this is like a very, very loose.
Yeah, it's very loose. Yeah, it's very loose, but it's still finite, right? It's not necessarily. So it's a very loose bound, and we'll see how we can tighten it up later. But yeah, the key point is that you can get away with finite number of neurons, and also the key point is that like these function spaces are sort of good for neural networks. Yeah.
Did you say what D?
D is the output dimension. Yeah. Okay. Cool. Yeah.
Can I see the full expression of VV norm for general case or?
I don't have it in the slides, but I can show you later if you want. Yeah, it's basically a total variation of the vector valued measure that you're using to parameterize your function. But yeah. Okay. All right. So how does this connect to weight decay? So basically now we can say that if you have f theta, which is a shallow vector valued neural network with k more than n times d neurons, and its weights minimize the following objective, which is the weight decay objective, then via the whole secret sparsity type of idea and neural balance theorem, we know that it's also a minimizer for the group lasso type problem, right? So therefore, it'll also, that function that you learn will also be a minimizer for this variational problem. So that tells us that neural networks that are sufficiently parameterized are living in this function space, these vector valued variation spaces. Okay, cool. All right. Okay, so now what does this mean? Like, why do we care about this particular norm or this function space? Does it really tell us anything interesting at all about what neural networks that are trained with weight decay are doing? And I'll argue that kind of does. So let's think about, if I have this norm induced on my function, and I know that neural networks, vector value neural networks trained with weight decay are trying to minimize this VV norm essentially, I can think about what kind of architectures would that really induce. So let's suppose I have a vector value neural network here, And I'm gonna show a couple of different ones, different varieties, and we're gonna look at their VV norm and what it corresponds to. So let's assume that your input weights are on the sphere still, and that the number of neurons you have is k, and that the output weights are like order of 1, okay? So if I assume that for each neuron I have very dense weights, so like think about the output weight v is going to be like a vector of all ones essentially, then the 2 norm of that is going to be square root d, and I have k neurons, so my VV norm will be on the order of like k times square root d, right? Okay, is that fair? So now let's say maybe I have a different kind of sparsity pattern in my neural network where every neuron, maybe I have sparse number of neurons that are activated, and for every neuron, it's like 1 sparse. So like every neuron, the output weight is just 1 and then zeros, right? So what that means is that every output depends on many neurons, different neurons, but those neurons are sparse, right? What that would correspond to for the VV norm is basically you would just have order d essentially, because it doesn't scale with the number of neurons you have. You have only a few neurons that are going to be active, but the ones that are active are only 1 and then 0. So if you sum those all up, it'll be like d, right? Okay, so that's sparse weights basically, not sparse neurons necessarily, sparse weights arbitrarily. And then another kind of configuration you could have for your architecture is one where you have sparse neurons. So in this case, I have every output depends on very few neurons, but the same few neurons, and every neuron contributes to every output. So you can think of now every neuron has like a 1 in every element of its output weight or output vector. So then what you would get is something on the order of like square root d. And this is obviously the smallest thing. So what it's telling us is VV norm is telling us something about kind of how much variation you're expecting to have on every output. Okay, so every output depends on the same but few neurons. Okay, so let me explain how we can sort of see this in a very simple experiment. Right. So what we did is we said, okay, let's look at a very simple problem where I have just 2 outputs, and the number of neurons I have is going to be very, very large, right? And what I'll do is I'll train this neural network on another neural network that only had like a few neurons, right? Maybe like 5 neurons or something. So that's like your teacher network. And then this is the student, and I trained the neural network on that data. And this is just like a regression problem. So it has 2 outputs. And then what I'm going to look at is I'm going to train once with weight decay, once without weight decay. And I'm going to look and see how many neurons are contributing to F1, how many neurons are contributing to F2, and are they at the same location, basically, okay? All right, so let's see. So when I do no weight decay, right, I train this problem with no weight decay. Here what I'm plotting is the bias. For each neuron, I have a bias and a weight. But since I'm in R2, this is a 2-dimensional problem, I can actually just write this, I can switch this like polar form, right? And I can just look at the angle that weight has, right? And all these dots are basically now the location of the neurons involved for F1 and for F2, for the first output and the second. So here you see that F1 and F2, they're very different neurons that are involved, and on the size of the bubble is the magnitude that's being attributed to that, or the weight that you're putting on that neuron, sorry. So yeah, so you see you have dots here that aren't on the right-hand side. You have some dots that are much bigger than the right-hand side, etc. Right? So it's very different type of thing going on, right? But when you do weight decay, you get a very different behavior. You see that the neurons are located in almost the exact same spots, right? It's literally exactly the same. So when you're doing weight decay, what you're doing is you're trying to find some kind of shared representation. These neurons are not acting in a way that's sort of disjoint. So you can think of like 2 things happening. If I have, say, capital D outputs, right? And I have n times d neurons, 2 things could be happening. One is every output is taken care of by n neurons, and those n neurons work in kind of like a disjoint manner. N neurons working for the first output, n different neurons working for the second output, etc., etc. And actually, if you take like all the work from scalar output neural networks and you just apply it to vector valued, like kind of naively, that's the sort of insight you would have. You would think that every neuron is sort of acting, or every output is acting on a disjoint set of neurons independently. But what we're showing here is that that's actually not happening. There's a real collaboration that's happening between the neurons in order to get a more sparse or parsimonious type of representation. Okay. So I said that this was sort of the central thing, that if I train with weight decay, then I know that my function that I learn at the end of the day is also the same function that minimizes this variational problem, and therefore vector valued neural networks trained with weight decay are functions living in this VV space. But I had a weird thing in there, which Karthik kind of pointed out, is that the number of neurons I need is very large, n times d, right? And n times d is like super big, even for very simple problems, like think MNIST, you have 60,000 times 10. No one's training with that number of neurons. And so the question is, can we do better? Is this really the reality of how many neurons we need? And that's what the second half of the talk will be about. So I'll go on to that. Okay. So now I'll talk about tighter bounds on necessary weight. So what the premise of this part of the talk is going to be like, say I've trained the neural network sufficiently parameterized. Now the question is, can I go back and ask, did I really need all these neurons? So it's kind of going back to that same thing I said earlier, right? I said the intuition is sort of that like maybe I need n neurons for each output. We showed that's not really the case. So can we prove something about how many neurons you actually need, even when you started off very, very wide? Okay. So let's suppose F theta is now a deep neural network and it solves the weight decay objective. And let's suppose that it's any kind of architecture you could want, but we're gonna zoom in and hone in on just one or an arbitrary homogeneous layer in that neural network. So I have a homogeneous layer, which takes me from some representation in R little d to another representation in R capital D. And the way I do this input output mapping is by taking this sort of weighted combination of representations learned in the intermediate layer, right? Okay. So now what I can do is I can look at my post-activation features before, or post-activation features in this layer before they get mapped to the next layer's features. Put those all into a big matrix. That'll be like R times capital N, right? And then likewise for the output features, it will be capital D by N, right? So I have these two basically matrix which hold my representations for every single training sample that I've trained on. And is that clear? And now before we said that when we train with, okay, so yeah, so we have this type of setup, and what I'm going to show eventually is that the number of neurons you need, this K hat here, let's say initially you had like, you know, a very large number of neurons n times d to get this perfect input output mapping. What I'm going to show is that basically you don't need K hat. You can get away with far fewer by exploiting the intrinsic dimensionality of these two matrices. Yeah.
Like one, the number of neurons here, when you say you need, it's like to perfectly fit the data, right? You have zero error. Or are you approximating?
Let's say the number of neurons I need for a particular error that I want. Let's say I've gotten it down to what I believe is the global minimum for my problem. Maybe that's interpolating, maybe it's not. But now I want to do the same type of, like, get the same data fidelity loss with fewer neurons.
I see, because you're always approximating a different network.
Mm-hmm.
Okay, but my
Wait, what do you mean approximate?
What I mean is like you already have a network that you're using to fit
data, yeah.
Mm-hmm. And then you're saying that I want to achieve the same loss as that network.
Mm-hmm.
And now how many neurons?
Same loss on the training data.
Yeah. Because my follow-up question is going to be like, how is this related to like memorization?
Yeah.
And I guess it's not, because you're not necessarily memorizing.
Yeah, you're not necessarily.
If your original network is memorizing, then you're bound to take the memorization bound and then either like blow it up. Or at least put it. Okay. Well, it depends on the bound, but yeah.
Yeah, well, yeah, all I'm saying is that I want some kind of input-output mapping to be retained. And I want that input-output mapping to be retained only on my training data set. I don't know anything about what's going on outside the training data set.
I'm curious now, if you take like existing memorization bounds and then apply this transformation to it, what happens?
I don't know.
Those bounds are already like close to that.
Mm-hmm. I don't know what you mean by memorization bounds, but we could.
Yeah.
Yeah. Okay. All right. So cool. Is this clear? What I'm basically doing. I have my post-activation representations, and my representation popping out at the next layer. Okay. All right. So before we said we had this whole discussion about how we can take the weight decay objective and we can play around with things, reformulate it, and showed that it will also be a minimizer for the following problem, where, or it'll also, the objective value obtained is the same as minimizing just the L2 or the group lasso regularizer, such that my input weights are unit norm. And now I want to put an additional constraint. I want to also make sure that the input-output mapping is retained. Okay, so that way I can ensure that I get the same representation from layer to layer, and at the end of the day, my loss will be the same. So this is kind of this reformulation is a consequence of the neural balance. Okay, clear? Okay, and then what I can do now, because of homogeneity, is I can automatically find this or make sure that this condition is satisfied by just messing with the input weights, right? So what I can do is I can change this problem such that I only look for VKs. I look for new VKs where the such that this is retained, where my input weights are now automatically always going to be on the sphere, right? So I would take my trained neural network, I'd have that one layer, I would normalize the input weights, push the scaling to the output weights, basically fix that representation now that I have, and then just train over my output weights in order to find a way to do the input-output mapping with fewer neurons. So this is like a consequence of homogeneity. Okay, and so now what's pretty interesting is that this problem here can be written in a more compact way, and it relates to an older problem known as the multitask lasso problem or group lasso regularization. And the question essentially boils down to, if I want to solve this problem, how many neurons or how many K hats do I need, basically? So it's like you're trying to find some kind of sparse representation. And this problem is kind of an old problem. The group lasso regularization first came out in this paper, and actually this guy, Yi Lin, is here at Madison, he's in the statistics department. So it all came full circle in a way. And then the multitask lasso problem, kind of written in this formulation, this goes back to like 2006. And when we realized this equivalence, we were really trying to look for, has anyone shown how many neurons I need, or how many, I keep saying neurons, this is just a linear problem, how many basically columns I need in V in order to make this optimal? Has anyone found any bounds? And it turned out no one had even really done that. So what we did is we proved this result and showed, and then reapply it back to the neural network case to prove the following kind of main result, which is this. So let's assume F theta is a deep neural network and it solves the weight decay objective. And then what I'll say is that for any homogeneous layer with input features phi and output features psi I, such that I have this input-output mapping for every single training data set or training sample in my data set, then there exists another optimal representation. So it has the same loss and gives me the same regularization value. I have another optimal representation with potentially different weights and different input weights and different output weights, where the number of neurons I need, K, is less than or equal to the rank of my output feature matrix times the rank of my post-activation feature matrix. And this is often much smaller than n times d. Okay, so this comes by instantiating the result from the multitask lasso problem onto the neural network case. Okay, so a couple remarks on this result. So first thing, what we're saying is we can get the same neural network, and not exactly the same function, but we can get a neural network that gets you the same loss or the same representations for every single training sample. But what's unclear is kind of like, now I have a compressed neural network. It's not necessarily the same function. How is the function different from the original one? Like in between training samples, how does the function, is it more wiggly? Is it smoother? Those questions are not really answered, and it's sort of an open question. We don't know how they're different. But yeah, most of the time you can get away with far fewer neurons than this n times d bound. And another interesting thing is that this K really depends on the data you have initially and the type of representation you learn. So if you learn very good, like low dimensional representation, you'll get away with fewer neurons at the end of the day. And this bound is much smaller than at the time, the tightest bound that we knew of. There was this paper from Decay who said that you needed n squared, which is essentially our thing that we said earlier. And this is oftentimes much smaller than that. And it explains a lot of the cases where we see that you can do really good with neural networks with way less than n times. Okay, yeah,
So Mr. The K hat is larger than the n times d.
yeah, that's to say it's at least large. Yeah, yeah, Jifan.
So my understanding is these feature matrices are based on V hat and W hat, not V and W, right?
Yes.
And are V and W full rank here?
No, not necessarily.
Not necessarily. Okay. So if you could imagine there may be multiple solutions like
Yes.
V hat, W hat. So like what's the tightest bound you can get, right? Like right here you could get a V hat and a W hat that's full rank, and that will give you n times d. But another function you learn could be lower rank. So yeah, just curious how to find the optimal one.
Yeah, so this bound is not actually tight. We're not sure if it's tight. When we tried this for the multitask linear problem, even that bound is not necessarily tight. It kind of depends on your data. It's hard to say anything more than this. And the weight decay problem is not unique. There can be multiple solutions. All we're saying is that there exists one that might have no more than this number of neurons.
I see.
Yeah. But we do have a lower bound as well, but the lower bound is not, the same as this, so it's not tight. There's a gap, and it's not really clear.
What does the lower bound depend on?
The lower bound, I think, depends just on rank of B tilde. I think I have to double check.
I think it should depend on C.
Maybe it's one of those two, yeah.
It makes more sense.
Yeah, I'll double check and let you guys know. But yeah, it's not really that, it's not a very interesting lower bound. It just basically depends on like generic data. Okay. Yeah, all right. So I'll conclude with just a small experiment we did to actually test this compression. So what we did is we took VGG19 that was pre-trained. And this has a lot of things going on, convolutions, it's a ResNet, blah, 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 or whatever's going on in there. And then at the end, we have just some homogeneous ReLU neural network, right? And that has 512 neurons. And so what we did is we extracted the feature representations for every single training data that you had, which in this case was CFAR10, put it into this really big matrix, call it psi tilde. And then we took the outputs, which would be just one hot vectors basically. And then what we looked at is what is the rank of this representation, right? It's 512 by 50K training samples. And when you see here is the singular values and the percent of energy captured by those singular values, which tells us that this matrix is about like rank 10, okay? Close to that. So therefore our bound tells us that we should need no more than 100 neurons, right? Because the output of matrix is rank 10, and this side tilde matrix is about approximately rank 10. So we should need no more than 100 neurons. And one thing I'll mention is that here, we don't actually know if this is a global optimal solution, right? We have no idea. It's trained pretty well, but not necessarily to the end. But we're still using our theory to see what happens. And what we find is we can get away with just 47 neurons in that last layer. And the results, if we look at like the compressed network and the new network, so this is V hat is the compressed, V is the original. We see almost no change in the train loss, and surprisingly, almost no change in the test loss or the test accuracy. And this is weird because what I said earlier was we don't know how the function has really changed. We just know that we can get the same input-output mappings on the training data set. And then we also have some more experiments where we did this for multiple layers within the network and for a different architecture, like AlexNet or something. So kind of an interesting result, and it seems like the theory does work for compression, and it's a very simple compression. It's just basically doing group lasso regularization. Yeah.
This might be a naive question, but to come to the bounds, you need an initial large arbitrary number of neurons, right? How do you decide that?
So yeah, so the reason we need a very large number of neurons is because we need to guarantee it's a globally optimum solution so that you can do all the equivalences between the types of formulations of the weight decay objective. In practice, we don't actually do n times d neurons. So for this experiment, we just took a pre-trained network and tried to apply our theory and see if it works. And it looks like it kind of does, right? Okay, cool. I have one more thing to talk about since this is kind of a, I guess a nice group. I want to talk about, this talk was all about like deep learning theory, and I think many of you guys have seen this recent paper. I thought I should talk about it, right? I'm talking about deep learning theory. And the question is, does this really tell us anything about how neural networks are working? Is this informative at all? And I think a nice quote from this paper David Donahoe recently dropped was, he says this, and I'll comment on it. It says, namely, I maintain that if counterfactually, empirical deep learning hadn't burst into prominence in 2012, and if counterfactually, transformers with attention hadn't burst into prominence in 2017, basic forces of a data science nature could still have produced many striking improvements in how we go about learning from data. And this script would be the same, but different stars would have been found to be cast in the storing rules. So basically he's saying that even if people hadn't stumbled upon MLPs and neural networks, and even if they hadn't stumbled upon transformers, we would still have all these really cool advancements in AI. And so essentially there's nothing super uniquely special about MLPs and transformers. And this is like, I don't know, I guess it's a good take. Maybe it's true. But at least for me, what I think is interesting is really if we can look at mathematically what these things are doing, what kind of functions they're learning, and what kind of representations are trying to squeeze out of the data, it could tell us something about what is good in a model, in a learning model, and what's not good at a fundamental level. And then we can kind of see what is the core of these transformers, neural networks that makes them work so well, and push us, I guess, to the next level of whatever AGI. So yeah, here's a link to the archive if you guys want to check out the paper and ask me any more questions. But yeah, thanks a lot for coming.
Quick question. So people said could be a DNN, which could be like any kind of model architecture, right?
Yeah.
But how does this depends on transformer, because transformer has this too big
Yeah.
feature, right?
Yeah, so that's a good question, because I was trying to see how I could do this compression thing on a neural network. You mean like when I do the experiment, or you mean how does the theory? So you have homogeneous layers in a transformer, right? You have a transformer and then it goes to an MLP. If you're assuming you have no batch norm and you're doing ReLUs, then you can apply this theory at least for the MLP and the neurons there. And even in the attention block, before you take the softmax, those WK and WQ matrices, they interact in a homogeneous way with the input. So you could also apply to that. Yeah. Assuming you're doing weight decay on those.
I have a question, Joe.
Yes. Yeah.
Yeah, so can you go back to the function space definition?
Yeah.
I'm wondering, is that a strictly more general definition of neural networks, or is this equivalent definition of the space of all neural networks?
Yeah, good question, good question. So yeah, in the paper we do talk about this. So past work, which is like Rahul's work, he characterized these variational spaces in terms of this rod-on TD2 norm. And to extend it to a vector valued setting, what you would do is you take basically you take the tensor product of these spaces to get a vector valued type of function space, and you'd have a new norm on that function space, which is not weight decay, but we show that it is equivalent to this VV norm. But it's kind of in the same way that like L1 norm is equivalent to L2 norm in RD, but they do very different things, right?
I think the question I had is slightly different. So like you could characterize the function of neural networks or shallow neural networks by just all W in R some D1 and then all V in some RD2, and then just the regular definition of an MLP, like V times activation of W transpose X. But what is this function space characterization more general than that? Is there any function in this space that's not covered in the traditional sense?
What do you mean the traditional? So like you have no regularization at all? Like you're saying no restriction on the size of these?
No, so I mean, when we usually define a neural network, it follows the form of f of x equals to v times sigma of w transpose x.
Mm-hmm.
So that's how I would usually characterize the function space of neural networks.
Yes.
Right? For any dimensionality, for any w and v, that's the function space. Is this space the same space, just a different way of writing it, or is this space more general?
What you're describing is not, no, this is, I think, more restrictive. Like you won't find necessarily arbitrarily large input weights and output weights. There is some restriction which is controlled by the norm, right?
I think if you take GFAN's definition and just make it finite width given for some arbitrary size, you make everything bounded, then this becomes more general.
If you make things bounded, then this becomes more general,
But is there any function in this space that's not expressible by a neural network?
So this is kind of like a variation space. It's not like the RBB2 type space. It's not a very general space. It's hard to say. Like I don't think so.
So
I think
I understand the contribution of this representative theorem is saying, well, I have a very general space of neural network right now, but only a subspace of that could be the solution of a global minimizer, and this is sort of narrowing down the space of the global minimizer.
Yeah.
Okay, cool. And for the host paper, like the RBB2 space, how do I place that?
So RBB2 space, if you have RBB2 space is for a single output neural network.
Yeah.
And if you have a single output in this space, then they're equivalent. And even if you take a tensor product of RBB2 spaces, it's also equivalent to this space in the sense of like the norms are equivalent.
I see.
Okay.
Good. There are no more questions I want to ask. I love the addition to the Donahoe.
Yeah, it's so timely.
I still have heard so much about it. I haven't played it as though that I like. I don't even know if I agree with it completely. Like progress would have been made, but I don't know if it would have been the same progress. Maybe we don't have GPD for writing papers and drafts. I don't know. But you said that if we can find insight into what makes transformers work or what makes these modern algorithms work, then we can like make that better or use that.
Yeah, sort of extract the core component,
right?
Yeah.
But from what I remember in like, for example, Misha Belkin's monologue, right? Like the speak without fear thing.
Sure, yeah.
Was it just felt like I still love theory for its own sake, but like it seemed like we don't have the theoretical tools to do that. Like, do you think that theory is anywhere near extracting what makes it work? Like
I don't know. I mean, in some sense, yeah, it depends on what you mean, but yeah, kind of. I don't know. And I don't think like the theory is really informing exactly what to do next as of right now. But I don't know if that's necessarily the goal of theory, right?
Yeah, no, I don't know like about the goal of theory because I think theory is good for its own sake. My question sort of is like, what's the most like impactful theoretical result that you can think of in the last few years in deep learning theory? So like most results I know like will either have like sort of an asymptotic bound or they'll follow the NTK regime. Or they'll assume things that don't occur in practice.
Yeah,
Like if you had to give me like a top 3 reading list of deep learning theory, because you've read a lot more deep learning theory than
I don't know, I'd have to think about it and give better answer, I don't know off the cuff like this, yeah. Best countries, I don't know, yeah, but. It's a good question, yeah.
I mean,
Okay.
it's interesting you're quoting this paper because when Rob was sharing this paper with me, he was basically saying, well, all that's driving the development of AI, it seems from this paper is saying there's 3 fundamental things: code sharing, data sharing, and competitive challenges.
Yes.
So that's what Dave thinks as the driving force of developing data science and AI. So yeah, like why theory?
I mean, he has the FFT example, right? In the article. It says like FFT and the Terravis algorithm, they were essential. So there are like some ideas that are essential. But yeah, not clear now what is that, what's this.
if there are no more questions, let's thank our awesome speaker, Joe. Hopefully we'll see you all in a couple of weeks. I think you can. Is that Yanis to start? Yeah. Okay, we have a speaker from UT Austin, Yanis Daras, will tell us about something. Thank you.